So yesterday you guys looked a little bit at separation of variables, and I got a lot of feedback from students on, wait, how do I know when I need to use separation of variables? Do I always have to use separation of variables? And it's just a process you go through to solve a differential equation. So this is actually an example, not from your packet, and you wouldn't need separation of variables here, but I'm going to show you how you could use it. So hey, we're going to solve a differential equation. So what does it mean to solve a differential equation? Or what does a solution look like? It's a function. Yeah, solutions to differential equations are functions. You're either going to end up with one solid function or a family of functions. Okay? So you're either going to go two routes. You're going to end up with a function or a family of functions. It's the family of functions deal. That's where you end up with plus c. So if they give you an initial condition and you can eliminate c, you can figure out what exactly it is, then you're looking with a function, right? You'll explicitly have a function defined. And if they don't give you an initial condition, you're going to have plus c in your answer, and you're left with a family of functions. I think they used some other language yesterday, so you had, let's see, the general solution. And you might have heard something like particular solution. That was the explicit one. So nonetheless, when you're solving a differential equation, you're not going to produce just one solid, ordered pair. It's not just one point. You're going to produce a new function or a family of functions. So this one just says, hey, there's a function y such that its derivative is 2x plus 1. Can you guess what that function is? X squared plus x. Now that's one of the functions that has a derivative of 2x plus 1. But ultimately, there's infinitely many functions whose derivative is x squared plus x. Whose derivative is 2x plus 1. So you need the plus c there. So c could be any number. Why is there what? So no matter what you make c could be any constant, any number. When you take, if c can be anything, then ultimately y is infinitely many functions. They're all related. They're all very similar functions. They only differ by a vertical shift. So x squared plus x is a parabola. So basically, if you took an equation of a parabola and added a number to the end of it, it's the same parabola. It just vertically shifted up or shifted down. Really, so similar parabola, it just lives somewhere else. But you didn't need separation of variables to come up with that answer. You could have used separation of variables. So separation of variables would say, hey, get your x's and your dx stuff together. So there's x, there's dx, and then get your y's and your dy's. Well, I don't see a y. So dy is just going to get put by itself. So somehow arrange this thing so you have the green stuff on one side and the orange on the other. And be sure, if you do have any fractions, dx and dy, neither can be in the denominator of those fractions. So how would you rearrange those? The oranges on one side. Yeah, dy equals 2x plus 1 dx. Yeah, maybe you got there by cross-multiplying. Thing is, you're going to see today, it's not always cross-multiplying. But use some strategy to separate the variables. Now, as a side note here, 2x plus 1 dx, what is the antiderivative of 1 with respect to x? That's x plus c. What do you suppose the antiderivative of 1 with respect to r? So that whole with respect to is kind of telling you what variable is going to show up. What about What's the antiderivative of 4 with respect to t? 4t plus c. Okay. So I'm doing that. You got the variables separated, and you're going to integrate both sides now. And I don't know if you remember from yesterday, but you know when you integrate how plus c shows up? Does plus c need to show up on both sides? Okay. So what's the, you're going to integrate 1 with respect to y. So what's the left side turn into? Y plus constant. Now I'm just going to put the constant on the other side. And the right side turns into x squared plus x. So the first way we did it, you just said, hey, what function has a derivative of 2x plus 1? And you just knew, without separation of variables, x squared plus x plus 1. Or x squared plus x plus c. Some functions, though, like let's say dy dx, let's say is negative x over y. I mean, you might as well try it. Hey, by the way, anybody know what y is? Such that when you take its derivative, you get negative x over y. You probably, like me, I don't know. You don't know. So at that point, what you're going to do is you're going to try to separate the variables, and then you integrate both sides. So when you separate the variables, I need you to get the yellows together and the oranges together, and make sure, if you've got fractions, dx and dy have to be in the numerator. Sure, cross multiplying will get you there. So you got y dy equals negative x dx. Variables are separated. What do we do to both sides? Nice, integrate, anti-differentiate. So the antiderivative of y with respect to y is so if this helps you guys, think this is a negative 1 right here, and there'd be nothing wrong with moving it out front. So you could erase this and put it here. So the antiderivative of x with respect to x. Nice, good job. And we got our plus c. So you better have c better show up on one side or the other. So now your job is, I think on this one we were given an initial condition. It was y sub 4 cap. So you could actually solve for c right now, if you'd like. I'm gonna wait. I'm gonna get y by itself, and then I'm gonna worry about solving for c. But either way, you'd be just fine, Quinn.
Is there ever going to be a third variable besides, or fourth variable besides y, x, and c?
Would there ever be a? Not that I could
So it's just
think of.
you're always be separating x and y on different sides.
Yeah, I mean, maybe they do it with m and t. You know, so.
Like x, y, and z.
No, not that I can think of. I'll look through my notes tonight. But so we sit here. I'm going to multiply both sides of the equation by 2. And something interesting is going to happen here. You really have two options at this point. And I don't mean to frustrate you, but I think after we get through it, you'll be all right. So this here turns, you can go one of two ways with it. Okay, option 1 is you're just going to write y squared equals, what do we got? Negative x squared plus 2c. Good, good. You don't need the 2. And I want to show you where it ends up going. Option 2 would be, like you guys are saying, y squared equals negative x squared plus c. So y still isn't isolated. What do you do to both sides? Square root y equals square root negative x squared plus 2c. On the other side, y equals the square root of negative x squared plus c. Hey, y is isolated. You've got an initial condition. If you didn't have an initial condition, you would be sitting with your general solution. but you've got the initial, so that allows you to pin down what C is. So we're going to take both of these. We'll put them on the next page. What was that initial condition? What? Okay. So in the end, when you do figure out what C equals, do you guys think that these two numbers are going to be the same numbers or different?
They're obviously not, because one is 3C and one is.
No, they'll be the same number because it's still just C.
Okay, well,
Yeah. Yeah, it's just
okay, we'll work it out.
Just divide it
going to be, but I don't see why they told us that it didn't make a difference. Then now you look at these and it would make a difference.
Yeah, and that's good. You're pointing out. So yeah, if they said it didn't make a difference and C is going to be different, then how is this okay? So let's work it down and solve for C. Yeah, which one do we use? So remember your initial condition. So what's X? Is X 4 or 3?
X is
4. Okay, so and Y is 3. So you got 3 equals square root of -1 times X is 4. So 4 squared plus 2C. Or you got 3 equals square root of -1 times 4 squared plus C. Just with the... So you're wondering about this format here. So it never did it say -x squared. I think the whole time it was sitting with a minus x squared. Exactly, yeah. Yeah, and that's what you'll notice, like a lot of times I'll write -x squared as -1 times x squared, just so I don't forget where it goes. So nonetheless, we got 3 equals the square root of, what is this, -16 plus 2c. And this one, 3 equals square root of -16 plus c. Isolate c, what do you do to both sides? Square both sides, okay, 3 becomes 9. Okay, you got 9. 9 equals -16 plus 2c equals -16 plus c. In the left-hand model, c is how much? Good job. And in the right-hand model, c is 25. So they ended up being different. We're like, well, how do we know which one to pick? Well, when you solve a differential equation, like you figure out what c is, and you're going to plug it back into your general solution. So notice how this guy here compares with this guy here. So take the respective c values, plug them in. So you're finding in either case, the answer is y equals the square root of -1 times x squared plus how much? 25. So if you missed that, we're just saying 25 halves if you plug it in. If you plug it in right here. Oh, geez. Or if you plug 25 in right here. Either's correct. You know, for me, I'd go with the right-hand model. There's just less to keep track of. But that's why I say, no matter where you are in the process after you anti-differentiate, you can plug in your initial condition and find C. But then, as you solve for Y, be careful. So we're going to see some problems. I'll wait for you. I know it's one of those days. We'll actually see some problems where it's really advantageous to solve for C in the very beginning. Like way back, even right here, you would have plugged in X and Y and solved for C. I don't think this was one of those, but you'll see some. Okay, so next problem. Which one do you guys want to do? 6? Okay. I gotta warn you, you're gonna hate me after number 6, but I'm here for you, and I'm just trying to help. Okay, so dy dx equals, that was number 5. All right, so 6. 6, you got to get the orange together and the blue together. So take a second and do that. Well, see, and that's why I think cross multiplication kind of sucks here. So you know you want dy's and dx's on the top. So for me, I would go, well, let's see. If I multiply both sides by dx, that gets the dx out of the bottom on one side. So I'm sitting with dy equals y over x times dx. And now the issue is I have, yeah, good call. Yeah. And I don't really like division, so I mean, yeah, I'll do it through multiplication. Same deal. So. And even at this, you're thinking life is pretty good until you realize when you anti-differentiate what shows up. Natural log, very good. Natural log is going to show up. So we're still feeling pretty good. Natural log of the absolute value of y equals natural log of the absolute value of x plus c. I guess even now, not a huge deal until you realize you have to explicitly solve for y. So you're going to need to get y by itself. But what is the log of y?
Well, it's 1 over y prime times y.
You're doing some like derivative natural log of y. You got to be able to strip off the natural log function. So which function is natural log's inverse? Yeah, e to the x. You have to exponentiate both sides. I think it's a word. We good now? Yeah, I mean, and the basic idea is if two quantities are equal, then e to those quantities will also be equal. So you're maintaining equivalence. So we can get into it if you guys would like to, but I mean, ultimately those are going away, and you're left with absolute value of y. What? Yeah, we have a way to strip off absolute value. And if you get some formal mathematician who would watch this video, they might be upset with how we handle it, but we're going to do it our way. It'll be fine. Now, the right side. I'm going to rewrite the right side, and I'm going to use some properties of exponents, which is like x to the a plus b is x to the a times x to the b. That's whatever, algebra 1 or something. You've got that property of exponents. That allows me to take the right-hand side. This is e to that large exponent, and you've got the addition here. So you got e to the natural log absolute value of x times e to the constant. Yeah, good call. E to the constant is just a constant. So we're going to be able to replace that guy with just c, another constant. Now, I know we haven't done anything yet with absolute value, but that's fine. So if you want to strip off the absolute value, just erase those vertical bars and put a plus or minus on the other side. exponentiate. Good. So I'm not gonna approach the initial condition. I'm not gonna use it until I have y isolated, and I'm one step away from y isolated. Imagine. What do you think I'm gonna replace plus or minus c with? Just another constant. You're right. So next we're gonna use the initial condition. I think we did have an initial condition. It was. What's this? Y of 2. It's 2. Yeah, y of 2 equals 2. So by the way, y of 2 is 2. Yeah. But ask me. I want to know what you're thinking though, so ask me your questions as you look. Okay. Plug in, yeah, 2 for x. Now wait. We should really look at this right here. Is there another way to write e to the natural log of the absolute value of x? It's just the absolute value of x. Well, you guys talked about how those functions are inverses, right? They strip each other away. I don't know why we didn't do that step back then. C is 1. Well, e to the natural log of anything is just that anything.
So, Mr. Lund, there's a rule when you have natural log of y equals natural log of x, that's absolute value y equals absolute value of x.
No. The absolute value, the absolute
Regular y equals absolute value of x.
the absolute value only showed up because of the anti-differentiation. Took the antiderivative.
So the antiderivative of natural log y natural log x.
All right, I'm going to let you guys keep looking and ask questions. Yeah, so hey, last thing, you're not going to see this. If you plug this into Wolfram Alpha, you're not going to see this as your answer. You just actually see y equals 1 times x. The absolute value won't be there. We're going to talk about it in the days to come, but we don't need to talk about it right now. It's really a result of, if you think about the absolute value graph, is it differentiable everywhere? No, not at 0. So, yeah, it might be shifted, but basically because of that point of non-differentiability, we end up stripping off the absolute value. We only get to use 1/2 of the graph because you can't extend this function past this point of non-differentiability. So, we'll talk more. It's not that interesting, but it's kind of important, but not a huge deal. So we'll go to number 8 off your worksheet. Awesome. dy dx y plus 5 x plus 2. All right, Mark, first step. What are you trying to do?
You were trying to get the y and the x dots.
Okay, sound like a calculus student, so how do you say? Sort of like isolate the variables, but separate the variables. We're trying to separate the variables. Well, so you got to get the yellows and the oranges. No, okay, fine. Separate the variables was the calculus way. So go ahead and separate the variables. You could say, I don't know, when you guys say cross multiply, I kind of die a little bit inside just because it's just not mathematical. It's just some dumb trick. I'm just, okay, so just go ahead and separate the variables. Don't copy my work, but I'm going to work on it up here. dy is, I got x plus 2 dx. What's that? You don't. It's fine. Yeah, we can handle it. So when we anti-differentiate, the left side turns into the natural log of the absolute value of y plus 5. The right side, anybody know? Right, what's the derivative of y plus 5 with respect to y? X squared over 2 plus 2x plus c. So the derivative of the natural log of y plus 5 with respect to y is 1 over y plus 5 times 1. So you just checking your work. So the left side was the natural log of the absolute value of y plus 5. And we know that when you're differentiating, you got the natural log function. It's 1 over what you got times the derivative of what you got. So 1 over y plus 5 times, well, what's the derivative of y plus 5 with respect to y? Just 1. So it's just kind of checking my work, make sure that I anti-differentiated correctly. Okay. So, what do you suppose we'll do to both sides? Exponentiate. We haven't decided if it's a word yet, but we're... Okay, before you yell at me when you look at the right-hand side, just think about exponents and how I could possibly do that.
That's just exactly what I did last time.
Yep, there you go.
You split up the x.
I don't have to. There's really no advantage to it. Miranda.
So I actually did that problem, and I just, like, from that step before, I just plugged in x and y, and then, like, I took the natural log of that side, and then solved it. Is that okay? Or
That's okay. Yep. I mean, when we get to the end and when we compare our solutions, the particular solutions, we should have the exact same solution. So, okay, now what do you do? What's going to get you closer to solving for y? Plus, okay, c is just a c. I'm going to strip these off here. I'll put a plus or minus on the other side. We can go 2 birds with 1 stone. That thing in blue is going to get replaced with just c. That'll be just c. What else do you suppose I'll do to both sides? Minus 5k. 2x minus 5. Okay, next thing to do is plug in numbers. What was the initial condition? When x is 0, y is negative 1. Okay. So plugging in 0 for x. Yeah, good job. E to the 0 is 1. E to the 0 is 1. So that thing right there gets replaced with 1. C equals 4. So your final answer is a function, and that function is y equals 4e to the x squared over 2 plus 2x minus 5. Okay, now, the last thing I'll ask you. The derivative of that function with respect to x is what? Oh, come on, come on. What was the purpose of solving a differential equation? So the derivative of the function we found is quantity y plus 5 times quantity x plus 2. That was what we set out to do. We set out to really design or find a function whose derivative was y plus 5 times x plus 2. And it was a pain, but we did it. Now we could go through and check it. We certainly could. I'm going to show you guys tomorrow how to use these things called slope fields to check your answers, but there'll be a way to check your answers.
Slope